Today we're going to be looking at Free Flag, which is a hard miscellaneous challenge from San Diego CTF 2022. The miscellaneous category is usually reserved for challenges that don't really fit into more common categories, but are still valuable for exercising the same problem-solving skills. Because this challenge is hard, in theory, we can expect some domain-specific knowledge to be required, as well as a certain amount of research and creativity. And this is also known as elbow grease. Anyway, the prompt reads, "We are so generous that we literally decided to give you a free flag on a challenge other than the sanity check." And then there's the attached file. If it wasn't clear, this file is an image which appears to be the aforementioned free flag. Despite technically being a flag, a picture of a checkered flag is not actually that useful for us. But there is one other thing about this image that draws my attention, and that would be the watermark in the bottom right-hand corner. It says, "Made with the ultimate flag hider," and it encourages us to try it out on the flag.sdc.tf domain. Now, this CTF isn't running anymore, so if you go to that domain, we won't find anything. For the purposes of this video, I went ahead and ran it locally in Docker so we can see what it would have looked like. On this page, without actually executing anything, it seems like we can upload an image as well as a flag or arbitrary text of our choice, and then hide the text in the image. So it seems like this challenge is a steganography challenge. Not only that, but because I'm pretending I don't have access to the source code of this web server, this is an example of black box steganography. Steganography is the practice of hiding secret information in normal files in such a way that does not rouse suspicion when inspected. Based on the setup for this challenge, it looks like the image that we've been given really does contain the flag. It's just been steganographically concealed inside of it. Our goal, then, is to reverse engineer how this hiding process works so that we can undo that process to extract the flag. What makes this challenge hard is the black box aspect. Black box stego is basically a slur in the CTF community, but I think we can still figure it out because we have been given access to the hiding program as an oracle, meaning that we can give it images and text of our choice to learn about how it works. There is therefore two stages to this challenge. Stage 1 will be using this web server to reverse engineer the hiding algorithm, and Stage 2 will be to write a program that can extract the hidden text from the image. To get started, let's hide a message in the simplest image that we can provide. I'm going to choose an image that is completely empty. That is, the red, green, blue, and alpha channels are all set to 0 for every pixel. If this algorithm is messing with the pixel values in any way, it should become obvious by looking at this example. The original free flag image is a PNG that is 512 by 512 pixels. I'm going to generate an empty image of the same size using the Python image library. If we open up a Python terminal and import PIL, we can generate this image in just a single line of code. If we type image.new, we tell it we're creating an image with red, green, blue, and alpha channels. We give it a size of 512 by 512, and we give it a default color value to set for every pixel, 0000. We can then immediately save this image to empty.png. Once we have the image, let's load it into the oracle and hide the message ABCDCBA. There's a few reasons why I chose this message that you'll see later. It gives us back an image that looks exactly the same. Well, aside from the newly added watermark. We'll just save this as hidden.png. Because the changes to this image are so small and subtle, I want to directly compare the values of each pixel to see which pixels have changed. There exist tools on command line Linux for comparing the bytes of two binary files, but that isn't what we want to do here because we're dealing with PNG images. The thing that you might not know about PNG files is that two PNG files that contain the exact same image down to the color values of each pixel and everything could have vast differences between their sizes and bytes. This is because different PNG encoders will often choose different compression algorithms when encoding the image. When I need to compare the color values of two images, it's better to convert the images to an uncompressed plain format, my favorite of which is PPM. On Linux, you can easily convert any image to PPM format using ImageMagick. The reason why I like this image format is because it's very easy for humans to parse. It's actually just an ASCII text file, and if you open it up, you can see that it's just a long list of pixel values as numbers, which is exactly what we're interested in. Unfortunately, we won't be able to use this version of PPM because it doesn't support transparency. Instead, we can use a slightly more obscure variation called PAM that the ImageMagick library uses as an internal format. It's less widely supported, but it's still simple enough that we can analyze it. I start by converting both empty.png and hidden.png to PAM files. To give you an idea of what this looks like, we can look at the top of this PAM file with XXD. Here we can clearly read that the image is 512 by 512, has 4 channels, and each channel is 1 byte. The end of this header is marked by a new line, followed by an immense number of zeros, which probably represent the channel values in each pixel. Since this image is empty, we see zeros here. 1 channel equals 1 byte, 4 bytes equals 1 pixel, so on and so forth. Next up, we can use the primitive Linux tool CMP, or just compare, to tell us the byte-wise differences between these two PAM files. When we do, we notice 2 things. Firstly, some of the pixel values at the very beginning of the file have changed. Where they were once 0 in the empty file, they are now non-zero in the hidden file. We also see some bytes at the end of the file that have changed, and this makes up most of the changes between the 2 files. The changes towards the end of the image are probably just the watermark that gets added. These changes at the top of the image are so small and minor, they probably have something to do with our hidden message. To get a slightly better rendering of what's going on here, we can use ColorDiff with the -y flag to display a side-by-side comparison of the hex dumps of both PAM files. When we pipe this to less, we have to pass the -r flag so that it will correctly display the colors from ColorDiff. Here it becomes a lot more obvious where the change data lives, at the very beginning of the pixel data for that image. From this, we can probably conclude that our message has been hidden into the pixel data starting at the beginning of the image. I now want to look at this pixel data in a slightly different way. I'm going to look at the hex dump of the hidden.pam image, but this time I'm going to seek ahead to where the pixel data starts, which will omit the header. I'm also going to display the pixel data as binary rather than hexadecimal, and I'm going to limit the number of columns to 4. Displaying the pixels this way, we can really start to notice some patterns. Firstly, each row of this hex dump is 1 pixel, and each byte is 1 channel of 1 pixel. So the first column is all the red values, and the second column is all the green values, followed by blue, and then finally alpha. Here's the first observation. Firstly, we can see that exactly 7 rows have been changed, which seems to imply that our message has been hidden in 7 pixels. If you recall, our original message is only 7 characters, so it seems like there might be a one-to-one relationship between each pixel and each byte of the original message. The next observation is that the only bits that have changed are the least 2 significant bits of each channel. The reason why I notice this is because it's actually a fairly common type of image steganography called least significant bit steganography. It means that however our message is being encoded, the bytes are being hidden in the least significant bits of each channel. The reason why this is chosen for images is because it only causes a small, usually imperceptible visual difference in the resulting image. If you were to instead tweak the most significant bits when hiding your message, affected pixel colors would appear drastically different. The last thing I want to note is a little bit more subtle but very pertinent to our solution. Recall that the message we hid was ABCDCBA. First, let's focus on the fact that the first character is A, and the last character is A. And we could see that both of these pixels have been set to the same value. A appears to translate to 10, 10, 0, 10. And we can see the same thing with B, 10, 10, 1, 0. and with C, which is 10, 10, 1, 10. This tells us that not only is each byte of our original message one-to-one with each pixel of the resulting message, the order of the characters in the message appear to be preserved. Additionally, the substitution from character to encoded pixel is monoalphabetic, meaning that the position of the character doesn't factor into the encoding. That's why the value of the pixel is the same, regardless of if it's at the beginning of the message or at the end. Just by looking at the bytes of this file, we've been able to conclude quite a bit about how the algorithm works. I would even propose that we know enough information to get started on the solution. To get started, I'm first going to use the flag hider one last time to generate an image that contains every character that I think might be in the flag. I'm going to include all the letters, upper and lowercase, all the numbers, and a selection of symbols that I think could be in the flag. We will use the empty image as a base, and we'll save this as encoding.png. Once we have this image, I'm going to start the solve script in a Python file where I'm going to store the exact same character dictionary in a variable. Next, we're going to import the good old Python image library so that we can read the data out of the image I just created. I'm going to open the image with pill, and we can iterate over the pixels in this image by calling image.getData. We only care about the pixels that correspond with characters in our dictionary, so I'm actually going to zip these two collections together, which will allow us to iterate over both in step. This is a good start, so we're just going to print the value of the character and the pixel that it corresponds with. You can see that it prints every character in our dictionary as well as the pixel value it corresponds with. Each of these pixels is a 4-tuple of red, green, blue, and alpha values, respectively. In other words, this is effectively a list of the mappings between each message character and the pixel that stores it. Next, we want to convert from this 4-tuple pixel to a value that contains the least significant bits of each channel, since those are technically the only parts of the pixel that matter for determining the character. To do this, I'll create a function called pixelLSB that takes in a pixel, and we will create an accumulator value called encoded and set it equal to 0, and then we'll iterate over each channel in the pixel and do two things. The first is to OR together the two least significant bits of each channel into our accumulator value. The second is that we're going to shift the accumulator by 2 bits to the left on each iteration. This should return a final value that only contains the least significant bits from each channel. We can test this out by printing the new value of the pixel after passing it through the pixelLSB function. Now we have a more useful mapping between the character and the actual bits written to each pixel. We can even visually see the one-to-one mapping with the ASCII value for the right curly brace. The RGBA value is 3213, and we can see encoded in the binary here, 3 in binary, followed by 2 in binary, followed by 1, followed by 3 again. So it's probably working. Back in our solve script, I now want to store a mapping between these values as a Python dictionary, where the keys are these encoded least significant bits, and the values are the character it corresponds with. You can probably see where I'm going with this, but I'll go ahead and just print the mapping for now. Here we can see the populated dictionary of encoded values mapped to the ASCII character values they correspond with. All we have to do in our script now is open the freeflag.png image and use our new mapping to convert the least significant bits in each pixel to their corresponding plaintext characters. We'll append these characters to a flag byte array, and we'll break from this loop if we have reached an encoding that we don't have a mapping for. Then at the bottom of the script, we will simply print the string stored in the byte array, and if we run the script, it should extract and print the flag that we were looking for.